Thanks everybody for joining. This time we have Felipe Rosso, who is going to tell us about localized thermal states and negative energies. Felipe, thank you. Take it away.
Thanks a lot for the invitation. I think this virtual seminar seems like a great idea. And yeah, so today what I'll be talking about is this paper that the title is Localized Thermal States and Negative Energy. This is the archive number, okay, 1907-07699. Okay, so let's get into it. So let me, there you go. So let me first tell you how I'm going to talk about this. I have a number of slides, and if at any point you have any question or some of the things I'm saying are not clear, feel free to stop me and we can talk about it, of course. I will start with an introduction, motivating what is this negative energy that arises in quantum field theory, explaining some general aspects of it, and trying to motivate what is it that I'm going to focus in. Okay. Then I will tell you this second section is the core section, which I'm going to tell you what do I mean when I say localized thermal states, and how is it that I can compute the energy and of these localized thermal states. I will then move on to consider this question. The question is basically how physical these localized states you can construct are. And there are reasons why this question is interesting. And finally, in section 4, I will discuss the holographic description of these localized thermal states. And I will try to convince you very briefly that it's actually quite simple, and it's just given by hyperbolic black holes in ADS. This is to say a black hole in ADS that has a hyperbolic horizon. And I will finish with some final remarks. When studying this subject, there were other interesting things I stumbled across the way that are in this paper that I won't have time to talk about, but I will briefly mention them in this final section. Okay, so if there are no questions, let me start with a general introduction and motivation. So what is the idea? The idea is that if you have a quantum field theory in Minkowski spacetime, the general thing is you expect to have an operator H that we call Hamiltonian, and this operator H will be the generator of time translations. And once we have this operator, we have a natural notion of energy, global energy, and for any given state, rho, okay, a state described by a reduced density, by an operator density, okay, you have this notion of energy, okay, and this energy, we expect this energy to be bounded below, and we choose that lower bound to be 0, okay. This is, of course, the fact that it is 0 is not strictly necessary, but it is actually convenient. And the fact is that the vacuum state of the theory, okay, it will be the state that has 0 energy, okay. So we have this natural bound on the global energy of any quantum field theory. This bound is true by construction. So when you have a QFT that also has a Lagrangian description, then you have a natural notion of a stress tensor, okay, by taking the variation of the action with respect to the metric. And when you can do that, then there's a particular way in which you can write a Hamiltonian that is given over here. It is an integral over a Cauchy surface of the stress tensor contracted with some Killing vector in an appropriate manner. So the question is, okay, since we can write the Hamiltonian in terms of this energy density, okay, functional, that it is given by the stress tensor, a natural question is, if I consider the energy density, this is to say the expectation value of the time components of the stress tensor, the question is this quantity positive or non-negative for any state that I can consider And since this is also a local quantity, this is to say it depends on Tnx, is it also true for any value of Tnx? This question is of course not new. It was considered many years ago, and the immediate answer is no. And in my opinion, the best way to convince yourself that this is true is to find a simple example. So if you consider a two-dimensional free-fermion massless, and you take this state psi, okay, that is given by this thing over here. Here we have the vacuum state and a two-particle state of some momentum p. This is basically the vacuum state A dagger, okay? And this alpha, what it does, it controls the superposition between the two states, and you can compute the energy density that you get for this thing. And this is what you get, okay? On the y-axis, we have the energy density, and on the x-axis, we have the space dimension. And as you can clearly see, there are regions in space-time where it is negative, okay, and regions where it is positive, okay. So from this very simple example, we see that this statement is not true. Yeah. Notice also the fact that when you integrate the energy over a cycle, which is say over here, the amount of positive energy is larger than the amount of negative energy. And this guarantees that when you integrate it over a cycle, you get a positive global energy, okay? Because that constraint has to be true. So I've shown you this for this very simple example, but you can actually show that for any reasonable quantum field theory, this is a general feature. This is to say, you can always find certain states for which the energy density at a point is negative, okay? So once we know that this feature is true, the next question is why should we care, okay? Why is this interesting? And I will try to give you two reasons. The first one is old, then the second one is more new. So the first one comes when you take a quantum field and you couple to classical gravity. What do I mean by this? I mean you take the quantum stress tensor of some matter field, let's say a scalar field, and you try to use that as a source to solve Einstein's equation. You can do that. And for the cases in which you have a state with negative energy density, what you find is that the geometry that you find after solving the Einstein's equation usually has some type of causality violation, okay? This is to say some closed time-like curves. It could be that, or it could be some other feature that violates causality. So it is certainly, if we're after a theory of quantum gravity that involves these quantum correlations, this seems like an important thing we should think about, and people have been thinking about this for some time. As you can see, this is a very old paper. And the second reason I want to give you of why this is interesting is people have, once this feature was noticed, people have been deriving bounds, trying to restrict the amount of negative energy that is allowed in a field theory. This is to say, we have to live with the fact that any field theory will have negative energy. We want to restrict how much negative energy we can actually have in a certain field theory. And this type of inequalities, you can think of the ANEC, if you have heard about it, the average null energy condition, or the QNEC. There are certain bounds that have been recently been looked into. And from these bounds, there are very interesting results one can derive. For instance, the conformal collider bounds by Hoffman and Malacena, they rely on the average null energy condition, that it's a bound restricting the amount of negative energy. Good. So let me tell you what is the objective, what is the aim of this paper. So the idea is to systematically, instead of focusing our attention on the bounds restricting the energy, I'm going to try to focus on the states. This is to say, I want to construct states a one-parameter family of states that interpolates between positive and negative energy for various CFTs beyond free field theories. Okay. Notice that the very simple example I just showed you is very nice, but it is of course for a free field. I want to see if we can do better than that. The idea is that in order to understand what is this negative energy, we have to understand the structure of the states which show this weird or this interesting behavior. And the way to do that is to construct these states. And along the way, we will find very interesting subtleties and, in my opinion, very interesting behavior that I think are very nice. Good. So now let me get to some of the details and tell you what do I mean by localized thermal states. That's the first step. Good. So let's consider a quantum field theory, conformal field theory in a couple of minutes, defining Minkowski spacetime. And let's take this a Cauchy surface, sigma, and let's take a region in this Cauchy surface A. Okay. And this sigma, let's take as a time at t equals 0 surface. And let us assume that the Hilbert space admits this tensor product decomposition. This is already, I wouldn't say an assumption, but this is not an innocent thing. Okay, we will see, I will show you in a couple of minutes that this assumption has some consequences that I will discuss in a minute. So the idea is a definition. What do I mean when I say a localized state, rho A? When I say that, I mean any density operator that is acting on this region of the Hilbert space, okay? More concretely, you can think of any operator that is localized, a local operator that is evaluated in the region A, okay? That's what I'm going to refer when I say a localized state. Notice my motivation is, we know that this negative energy density is a local feature, okay? Therefore, if we want to actually construct states which show this feature, it seems like a wise thing to do to consider states that are somewhat localized, okay? Because they are more likely to present this behavior. So let me give you a concrete example. If let's take a two-dimensional field theory, let's say this vertical direction is time, and this horizontal direction is space, x. And let's take the region A as this red segment that we see over here of some length r, okay? This is the segment. An important thing is that causality and unitarity of the theory means that this localized state, rho A, is not only defined on this red segment, but it is actually defined on this whole causal diamond, okay? So, yeah, that's an important thing to keep in mind. These states are localized in a whole space-time region, okay? They're not only defined in a region of the Cauchy surface. Good. The idea is we want to construct a one-parameter family of states, and we know that a very simple family of states that we usually consider are thermal states, okay? And usually they are very simple to study, or yeah, that's the idea. So the question is, can we define a thermal state that is only defined in this region, okay? And the question is, kind of yes, but in some cases. What is the idea? The idea is that if you have a simple enough region so that you can define a time-like evolution, okay, given by a parameter tau, a real parameter, such that for any point in the space-time region we're considering, this transformation leaves that point inside of that region. What do I mean by this? If we go back to this case, if I have a set of points that are located in this area and I apply the transformation, that transformation can move those points all around the blue region, the blue diamond. However, that transformation shouldn't move the points outside of the diamond, okay? The idea is that there are certain cases in which you can construct this type of evolution, and it is important that this evolution is timelike. In general, this is not true. Okay, if you take an arbitrary region in a quantum field theory or on a conformal field theory, you will not be able to do so. However, it is true for the case of the half space, okay, whose causal domain is the Rinder wedge or a ball, okay. In those simple cases, you can actually do that. So when you in the cases where you can do that, you can define this operator k of tau, okay, that it is an integral of this component of the stress tensor integrated. Notice that it is integrated only over the region A, okay, and this is the operator that generates this flow in this tau parameter, okay. So once we have this, we have a natural definition of a localized thermal state given by this equation over here, that it's very natural in some sense. It's simply the exponential of minus beta. Beta is some type of inverse temperature of this generator, okay? This generator that generates time translations in this region, okay? Remember, the region that we're going to consider is the half space or a ball, okay? Actually, in this talk, I'm only going to talk about the ball, since I think it's the most interesting result. Yes?
You already assume that you are in a conformal field, right? It's like the result for half space is completely universal, but for a ball, you have to do a conformal summation, right?
I'm not hearing you very well, but I think your question is, so for the half space, it's a universal result. You can consider a QFT, and that's fine. For the ball, you have to consider a conformal field theory.
Yeah, that was precisely the point I wanted to make. Yeah.
Oh, great. Yeah, that's totally true. Yeah. Any other questions?
Yeah, I mean, so usually one says that the Hilbert space does not factorize in quantum field theories. Do you neglect this issue, or is it relevant here, or?
Yes, great question. So what I'm doing for the moment, I'm neglecting this issue in the same spirit of the calculations people do when it comes to entanglement entropy, okay? In that case, that is the most usual approach. And we will see that neglecting this issue is not free. There will be some consequences in a couple of slides that actually the consequence will be some type of divergence that will appear in the quantities that we're going to compute. And yeah, it is a choice we're making, and there will be consequence. Yeah, it's an interesting point. Good. So this is what I mean by a localized thermal states, and from now onwards, I'm going to consider the case of the ball, since I think it's more interesting. So let's consider a ball B, and let's first discuss this modular flow, this flow given by tau. How is it that what is it given by? And this has been known for a while now. And the way in which you construct this tau coordinate is the following. First, you define this coordinate omega, that is simply a null coordinate, okay? This r is the spatial radial direction in Minkowski. This t is the time, the Minkowski time. And you define this change of coordinates. That's not that bad, it's pretty simple. U is a positive coordinate, okay? And tau is this parameter that will give us a flow, okay? One of the first references, not the first one, but one of the most famous reference where this transformation was considered was in this famous paper by Cassini, Wirth, and Myers. And when you consider this change of coordinates, you apply this change of coordinates in the Minkowski metric, okay? You take the Minkowski metric, you simply do this change of coordinates, and this is the metric you get, okay? What is this metric? First, notice that we have this conformal factor, okay, this omega square, that depends on both tau and u, okay? And we have this time-like direction tau, and we have this hyperbolic plane, okay, of radius r. dh is a hyperbolic plane, a unit hyperbolic plane. So what is this metric? This metric is nothing more than the Minkowski metric. I haven't done anything but a change of coordinates. However, from the nature of the change of coordinates, it is not hard to convince yourself that this change of coordinates does not cover the whole Minkowski spacetime, but only covers a region. And actually, the region it covers is precisely the causal domain of a ball. Okay? So this weird-looking metric is nothing more than a metric that describes the causal domain of a ball. And notice that we naturally have this time-like translation given by tau, which by construction leaves the region unchanged. This is to say, moving tau does not take you out of the causal domain of the ball. Another point that I think is important is notice that this metric is non-static, right? Because we have this conformal factor that explicitly depends on tau. This means that tau translations are not an isometry of this geometry, okay? This means that the thermal states that I have considered are not thermal in the usual sense. This is to say, are not given by the exponential of a Hamiltonian of a conserved quantity. What they are thermal with respect to, they are thermal with respect to the KMS condition, okay? For those familiar with the KMS condition, it's a generalized notion, okay, of thermality that is most often used in the algebraic approach, okay, of quantum field theory. So it is in that sense that these thermal states are thermal. Good. For this particular case, we can actually write the localized thermal state explicitly, and we get this expression. Okay, here we have exponential of minus beta, and this over here is the operator that generates tau translations. Okay, for those of you familiar with modular Hamiltonians, this is practically the modular Hamiltonian associated to the vacuum and above. A couple of comments regarding this operator. As I just said, there's a special value of beta, that's 2 pi r. And for this particular value of beta, this thermal state, this localized thermal state, is equivalent to the Minkowski vacuum reduced to the ball. Okay, what do I mean by this? Is this expression over here. If I take this state, this is equivalent to taking the Minkowski vacuum, okay, 0m, the Minkowski vacuum, and tracing over the degrees of freedom in the complementary region, okay? So this is basically a consequence of the Soniano-Wickman theorem, and this is basically the Unruh effect. It's not that mysterious. Good. So from this, there's an immediate result that follows. If you consider the energy density that I will note in this way, okay, of this localized thermal state for arbitrary values of beta, this is the localized thermal state times the TP component of the stress tensor, and we take the trace. There's a particular value of beta equals 2 pi r, where this energy density vanishes. And the reason it vanishes is basically because the localized thermal state is equivalent to the vacuum. And the vacuum has zero energy density, okay? So for this particular value of beta, the work is done. There's nothing for us to do. So the main question, technical question that we will have to address is what happens when we go away from this particular value, okay? And this is where the most technical things come into play, although it's not particularly complicated. So let me recap a little bit. What have I done so far? I have given you a definition of a localized thermal state as a state that is defined just in a given space-time region. And the state is thermal with respect to the modular flow, okay, this generalized flow that in some cases it's local and you can define in a very simple way, like in the case of the ball, where you have this structure. So far, I have considered a general d-dimensional CFT. Yes, so now I want to talk about how do we compute this quantity over here. Notice that actually computing this trace might be somewhat challenging, okay, because the trace is over this Hilbert space, okay, that is only about tracing over the degrees of freedom in the ball. So it's not the most standard thing. So the first thing we'll do is to map this to a more usual setup. And the way in which we do that is the following. This is the metric that is describing the ball, the causal domain of the ball. And it is very suggestive to consider a binary scaling, which removes this factor over here, so that the transform metric is this one over here, that simply describes a spacetime of R across a hyperbolic plane. This is convenient. Why is it convenient? Because under this transformation, the localized thermal state is mapped to a real thermal state. Noted that this is already evident from this metric over here, from the transform metric, where now tau translations are an isometry of the field. Okay, we see that there is no tau dependence in the metric, meaning that as you translate over tau, the metric, it is a symmetry of the metric. What is the consequences regarding the state? The consequences are that this state that we have over here is now an ordinary thermal state, okay? It's the exponential of the Hamiltonian of the field. And computing the energy density of a thermal state is much more standard than the initial computation that we were interested in, okay? Therefore, if we follow how the energy density transforms under the conformal transformation, we will be able to obtain the energy density of the localized thermal state in terms of the energy density of an ordinary thermal state. And this is what you can do. And this is the result. Okay, let me break this expression since it might seem complicated. The only thing I've done from here to obtain this expression is a conformal transformation. There's nothing mysterious. So we have two contributions, you could say. On the one hand, we have the space-time contributions that are given by this thing over here. That depends on the conformal factor, that is this thing over here. And notice that the omega plus minus are these coordinates, okay? They are simply null coordinates in Minkowski, okay? So the space-time dependence of this expression is given by this conformal factor and this factor over here, okay? Notice that all the space-time dependence that we have over here is non-negative, okay? It's positive, and yeah, so that's an important thing. And apart from that, the other contributions that we have in this expression are given by this quantity over here, okay? This subtraction. And what do I mean by this notation? What is this? This is simply the energy density of the thermal state in the hyperbolic background, okay, in this background over here. So in order to really obtain this expression, we still have to compute this quantity, okay? And this will be a little bit more complicated. But let me, was there a question, sorry?
So in this derivation, beta is a parameter, right? Like you're free to pick beta whatever you want, and R is also a parameter you're free to take it whatever you want, right?
Yes, exactly.
So this epsilon bar of beta minus epsilon bar of 2 pi r is something that is that is fixed, right? Like in terms of these two parameters.
Yes.
Positive or negative, and then the rest is an overall factor that is positive. Okay.
Yes.
But in general,
yes.
This is going to look like an excited, I mean, this is going to look like an excited state from the point of view of the Minkowski space.
It's going to look like an excited state. Yes. Yes.
I remember, well, I remember a paper from like, well, there's about 10, maybe 12-year-old by Gapser, in which he looked at the black hole spacetime, so the thermal state. And then there was a, oh yeah, so there's a conformal transformation. There's a binary scaling. There's a binary scaling from a theory on sphere cross time to a theory on Minkowski space. So you can consider the thermal state on a, so it's a thermal state on a sphere across time, and the thermal state on a sphere across time looks like a time-dependent, becomes a time-dependent state in Minkowski space, and this was called conformal sorting flow. So what you want to do is kind of similar, somehow like spiritually similar, because you want to talk about not like inhomogeneous states where inhomogeneity and possibly time dependence comes from the Bailey scaling, right?
Good.
All right.
Good. Good. Yeah. Yes. I agree. Good. So it is clearly it's not homogeneous. Okay, it has some I wouldn't say complicated, but some space-time dependence, and the whole dependence on the beta factor comes from this quantity over here. This factor it actually comes from the anomalous transformation of the stress tensor, and this is the ordinary factor. So let me make a few comments about this expression. Since, as we can see here, the space-time dependence, this factor is always positive, or at least non-negative. The sign of this quantity is completely determined by the sign of this one, okay? And notice that this is the energy of a real thermal state. So if we assume that the energy of a thermal state increases as you increase the temperature and decreases as you decrease the temperature, you can think of this as a stability requirement of the thermal state. This already means that for beta larger than 2 pi r, the energy density of the localized thermal state will be negative, okay? And for the opposite regime, in which beta is smaller than 2 pi r, the energy density will be positive, okay? So from this expression, we can already see that we are getting to what we wanted to get to. Mainly as we move beta, we're going from positive to negative energy density, okay? However, we still don't have, from this argument, we don't have the explicit way in which this interpolation occurs. In this sense, we don't have the explicit beta dependence of these states. And the next comment I want to make is, let's consider for a moment the two-dimensional space-time, okay, in which it is the region is given by a segment. It's the analogous figure I showed you a couple of minutes ago. It's given by a segment, and this is the causal domain, okay? So what you can do is you can plot this space-time dependence for this case, and this is the graph that you get, the plot that you get. Blue means small, orange, yellow means large, okay? And what we see over here is that when we go from the center to the boundary, the energy density starts growing, okay? And it diverges at the boundary, okay? So this goes back to the question I had at the beginning of the talk regarding this factorization that I'm assuming of the Hilbert space. And here we see the price that we're going to pay. The price that we're going to pay is that the energy is going to diverge when we approach the boundary, okay? From a practical perspective, you can interpret this as telling you that the factorization that you have assumed is not really true. Yeah, so in a minute, I will consider this divergence again, because you might be worried about this, right? Because in the particular case where beta is larger than 2 pi r, what you get is that this factor over here is negative, and when you approach the boundary, it goes to minus infinity, okay? Therefore, we get in a state that as you approach the boundary, it has a negative, it goes to minus infinity, the energy density, which seems something weird. So we will consider this, we will address this issue in a moment. Before doing that, let me show you.
Sorry, can I ask a question about that figure?
Yes, totally.
I'm confused because the factorization issue is related to the divergence of the entropy.
Yes.
The edges of this region. I would have thought by analogy with you know, what happens in Riddler space, that the divergence you're seeing in the energy is analogous to the fact that as if I go anywhere near those boundaries, it's like performing an infinite boost.
Yes, I completely agree. That's another interpretation you can make. Let me tell you a little bit more of what do I mean when I say that it is related to the factorization of the Hilbert space. So when you want, in the particular case, using, there's a nice calculation by Doker, I think, in which he computes the entanglement entropy of a sphere. And he's able to do that by considering basically the same quantity that I'm writing over here. Starting from the energy density of the thermal state, there's a very simple way of going from here to the entanglement entropy of the vacuum state reduced to the bulk.
I see. So there's a relationship between this energy density and the entropy.
Exactly. Exactly.
Or I need to check this paper by Doker.
No, I'm not going to discuss it, but you can check. I think the title of the paper is entanglement entropy for even sphere or something like that. I can send you a link there. But okay. Yeah, I understand this from a practical perspective, in the sense that this same divergence you can associate to the same divergence that you get in entanglement entropy. Therefore, I relate that to the factorization of the Hilbert space.
Okay. Oh, that's interesting. Okay, thanks.
Good. So before addressing this divergence, notice that we still have some work to do, and it is actually the hardest work, is to compute this quantity over here. This is computing the thermal energy of a conformal field theory defined in this curved manifold. Okay, so it is a standard calculation, but in some cases it's not particularly simple. So let me show you that there are cases in which you can actually do it. The simplest case is when you consider a conformal field theory in 2 dimensions. And in that case, you can analytically completely do the calculation. And this is the expression we have. C is the central charge. And T is this dimensionless temperature I have defined over here. As you can see, when T is equal to 0, the energy density is negative. When T is equal to 1, it vanishes. And as you go to larger values of T, it is positive. So we explicitly see the dependence of the energy as a function of the beta parameter. The reason this calculation becomes very simple and general to do for the 2-dimensional case is that the hyperbolic metric in 2 dimensions is just the real line. So this is R cross R in this case. If you consider a scalar field in this manifold, you can also do the calculations for generic spacetime. This is a calculation that's done in the paper. In the particular case of 4 spacetime dimensions, it's very simple. It's given by this expression. And you have analogous expression in higher dimensions. And you can also consider holographic CFTs, and you get some other dependence that I show over here, where you see that the dependence on the T parameter is a little bit more complicated. Why do I? Yes.
I have a question. Like maybe you said it, but I have to leave for a moment. So I know that like if you look at theories on say like in 4 dimensions like R cross S3, then there might be different phases depending on the temperature, right? So for example, like if you take like anyone for superior on a sphere, right? Then there's going to be low temperature phase and there's going to be high temperature phase, right?
Yeah.
And the thermodynamics, I mean, like what you get as an energy density is going to depend on which phase we are, right? So for example, like the black hole, so like the deconfined phase is going to be thermodynamically unstable at sufficiently low temperatures, etc., right? And over here, you talk about theory on R cross hyperbolic disk. So, I mean, like, is there such an issue or not? Because, like, in principle, hyperbolic disk is characterized by the curvature scale, right? I mean, I think the curvature scale is related to the parameter R. And as a result of this, in principle, I can imagine that there might be something interesting happening as a function of R times beta when we look at thermodynamics. Is it the case or not?
That's a very interesting question. To be honest, I haven't paid much attention to that, in the sense that I have simply considered this is a very straightforward calculation. You have the thermal state, a very concrete thermal state, you have the stress tensor, and you take the expectation value. But it is definitely an interesting calculation. as far I'm concerned, from holography, you can consider the phase transition of the hyperbolic black hole, and if you just have the hyperbolic black hole, you don't see a phase transition when you have this spacetime. So in that case, there is no phase transition. However, if you add a scalar to that black hole, there is a phase transition. So yeah, in that case, it might be something interesting to look into.
Well,
Yeah.
I'm just saying all this because then if there are different phases for different temperatures, only for some temperatures you're gonna get this negative, right? And like this was that's why I was asking.
Yeah, yes, I agree. I think it's a matter of finding that phase transition that I don't see any simple way of understanding. I mean, where that phase transition could be, or if it is actually there. I mean, the simplest way to analyze that phase transition that it comes to my mind just now is using holography, okay, looking at the thermodynamics of the hyperbolic black hole. And in that case, when you just have the black hole, you don't have a phase transition. That doesn't mean that there isn't some other setup, more complicated setup, in which you can find another way, another space-time in which you actually have the phase transition, but at least in the simplest one, you don't have a phase transition in the holographic setup. But I mean, it's definitely an interesting question. Good. So what I wanted to show you with this is simply that you can compute this and get explicit expressions. So let me now go back. Oh, yeah. So I should be, how much time do you have? 5, 10 minutes?
I have about 20 minutes, more or less.
Oh, beautiful. Yeah, great. Okay, good, perfect. So now let me address the other question I told you about, this divergence that we have at the boundary, that raises the question of whether these localized thermal states that I have constructed, that I have studied, are physical, okay? The reason, let me tell you again, the reason is that for this value of beta, the energy diverges to minus infinity as we go towards the boundary, okay? So in order to address this question, the question of whether these states are indeed physical, what we are going to do is we're going to consider an observer that it is inside this region, inside the causal domain of the ball, and consider the energy measured by this observer, okay? More precisely, what we're going to consider is this quantity over here, okay? Is the energy observed by the state that, yeah, the energy observed by the observer in the state rho beta, okay, rho beta. And the way we're going to consider that is by giving an integral over time. We're going to consider an observer that is fixed at the origin of the sphere, okay, and that is, it just remains there, okay. So when we consider time, it's just an integral from in the time, and the guy simply remains there. And we're going to consider this integral. This is the energy density evaluated at the origin. And we have the integral over this phi function, okay? What is this phi function? This phi function is a non-negative function that characterizes the measurement apparatus, okay? And there are certain requirements that it has to satisfy, okay? The first one is that this phi function has to be non-negative. Yes. Was there a question?
No.
No. Ah, good. This phi function has to be non-negative, okay? And it has to be compactly supported in the causal domain of the sphere, okay? It has to be non-negative because we should think of this function as a weight function. And it has to be supported in the causal domain of the sphere because this is where our state is properly defined, or at least defined. And the second thing it has to satisfy, it has to be a smooth function, okay? And the reason where this is required, we will see in a moment. When people have considered bounds for this type of quantity, okay, for bounds for the energy measured by an observer, The bounds on quantities like this are referred as quantum energy inequalities, and they have been studied for 20 years or so. And whenever people bound this type of quantities, it is a requirement that this function is smooth. So let me show you one of the simplest bound people have derived, and it is the following. Let us consider an arbitrary two-dimensional CFT, okay? And on the left-hand side, we have the quantity I have just defined and I was talking about, okay? And this quantity gives the energy measured by the observer, okay? And on the right-hand side, we have a negative quantity that depends on the central charge, and it depends on the weight function we are considering, okay? This is, of course, a positive quantity, so on the right-hand side, we have a negative quantity. So what is this inequality telling us? This inequality is telling us that the energy measured by the observer can be negative, but can be negative up to this particular value, okay? And the actual value that we have on the right-hand side is determined by the central charge. This is to say the particular field theory we're considering, and the weight function that we have. And this bound was very rigorously derived by Fischer and Holland in 2004. And it is very important that this function is smooth, okay? So what is the strategy? The strategy is to plug in this left-hand side the energy density that I just showed you for a two-dimensional CFT, and see if this inequality holds. And when you do that, you can rearrange this inequality in the following way, and you get this quantity. We have an integral over this parameter b. B is simply a rescaling of the time coordinate, and we have this operator acting in between, okay, where this operator is simply a derivative plus this function, okay, this complicated function. And the next thing is that this inequality can be rearranged in this way, where here we have d dagger d, okay? So this is an explicitly positive operator. Therefore, this inequality holds true, okay? So what have I done from here to here? I have plugged in the energy density that it is divergent, okay, for every value of beta. And I have seen that that divergence is actually smoothed out by the function, by the wave function, such that the bound always holds, okay? This means that despite of the appearance of these energy localized thermal states, that their energy density is like weird and there might be something wrong, we find complete agreement with this type of inequalities. And you can actually show that when beta goes to infinity, this is to say the zero temperature case of the localized thermal state, this bound is saturated, okay? So this localized thermal state we have considered saturate this general inequality. Good. So what about higher dimensions? So when you have a free scalar in even space-time dimension, there is an analogous inequality to the one I just showed you. And you can do a similar calculation. In that case, it is not as neat as the two-dimensional case, but it is straightforward. And you still find agreement, okay? The bounds are always satisfied. And what is the conclusion we get out of this? We can conclude that there is no evidence that these localized thermal states have more negative energy than they are supposed to have. Therefore, saying that the structure that they have is reasonable or fine. Good. Yes. Good. So now let me get to this this final section, in which I'll briefly discuss the holographic description of this localized thermal state, and I will show you that it is actually very simple and given by the hyperbolic black hole, which from the discussions that we have so far, it's like not that crazy. Yes, there was a question.
No.
No, great. Good. So this might seem completely unrelated, and it is unrelated. So when you have black holes in ADS that have a hyperbolic horizon, okay, it has been long known that the mass of that black hole, it is negative for some region of the parameters. This is to say there's a value of the horizon, for the radius of the horizon, for which the mass of the black hole becomes negative. Okay, this has been long known, and notice that from the gravitational perspective, this is somewhat weird, and it's not clear how to interpret this result, right? It is not clear what's the meaning of this negative mass of the black hole. What I want to argue, what I will show you in a couple of minutes, is that this negative mass of the hyperbolic black hole is actually completely related to the negative energy of the localized thermal states that we have just discussed. So the question is, can we relate this to the localized states in the CFT? And the answer is yes. And this this can be schematically shown in this diagram that you have here on the left. Let us start with this on the right-hand side. So on this little box, what we represent are the localized thermal states in the ball. Okay, these are the states we discussed at the beginning. Okay, and so far I've shown you that applying a conformal transformation, we can map this to ordinary thermal states in the hyperbolic background. Okay, where the temperature in one side corresponds to the temperature on the other side. And once we have a thermal state in the hyperbolic background, we have the standard ADS-CFT dictionary, okay, that tells you that the thermal state in the hyperbolic background is dual to a bulk hyperbolic black hole, okay. So if you follow under this set of maps, what happens to the energy density? You see that states that have negative energy density, okay, are completely mapped to the negative mass of the black hole, okay. The black hole is just given by an integral of some quasi-local energy density. So from this perspective, we see that the negative mass of the black hole is not only expected, but it is actually something that's necessary. And the easiest way, or well, a natural interpretation you can give of this is that the mass of the hyperbolic black hole is capturing the negative energy excitations that are located in the dual field theory. Okay. So yeah, this is a very nice picture which gives you a way of interpreting this result that in the gravitational setting it's like weird, and it's unclear what's the meaning of it. Good. So let me give some final remarks. What we have done, we have constructed this localized thermal state in the causal domain of the ball, and we obtain explicit expressions for its energy density for a wide variety and range of CFTs. Okay. As the inverse temperature of this localized thermal state changes, the energy interpolates between positive and negative energy. This gives you a simple way of studying the transition between one regime and the other. What we found is that the maximum amount of negative energy that these states can possess is in perfect agreement with the bounds that are present in the literature. They are completely physical. And moreover, for holographic CFTs, this negative energy is mapped to the negative mass of this ADS black hole. So in the paper, I've also worked out the case for the half space. This is to say for the Rindler region, and you get an analogous set of results, very similar. And I haven't done the calculation for other cases in which you can actually do the calculation. This is to say, if you consider a conformal field theory that's in a fixed background, cylindrical background, and fixed ADS background or a fixed TS background, you can do a very similar construction. and you can compute the energy density of these localized thermal states, and you should get similar results. So these are other setups in which you can apply a similar construction that is useful for studying this negative energy. Some of the things I haven't talked about that are discussed in the paper and I think are interesting. So Cassini, Wirth, and Myers, long ago by now, in 2011, they gave a proof of the holographic Ryuta-Kayanagi formula for the entanglement entropy of a ball. And from using this construction I have explained, there's a very completely analogous construction you can do for the half space. And you can show the RT formula holds for the half space and everything works out. And another interesting thing that that you can see in this construction is that what you can do is you can consider a separable state, okay? You can consider a state given by this thing, okay? Where here rho s is a global state defining the whole Minkowski spacetime. And you can consider constructing this state, and what you can show is that in order to construct a state like this, you require an infinite amount of positive energy. This is to say, if you want to consider a state that is separable, okay, that notice that this state has no entanglement across the partitioning of A, then the only way you can do that is by putting an infinite amount of negative energy. This gives a very precise realization of something that's usually said, that it comes from the fact that entanglement is always necessary to construct states in a continuum quantum field theory. So you can make the statement more precise in the sense that you can show that if you wanted to construct a state that has no entanglement across a given partition, the only way in which you can do that is by putting an infinite amount of energy into the system. So there are some couple of calculations regarding that issue in the paper. Yes, so I am done. So thank you. Thanks a lot for listening.
Thank you, Felipe. Are there any questions? Maybe from our viewers online? Yeah, we already had some questions. So if there are no further questions, let's thank Felipe again for this great talk.
Yeah.